Okay, good morning and welcome to Action Potential. There was one very interesting email. Means I was really happy about about your honesty. This gentleman is of 22 years and what he has said is that practically now I am starting my medicine. So so that's what he is worried about, that my peers, they are now either in final year or they have moved much ahead in medical science. So how come, what should I do? So many thoughts are coming. I would just say one thing. Van Gogh, he's a he was a very nice painter, but at the age of 69 he started painting. At the age of 69, till that point he was practically doing so many things, but nothing was getting successful. So at the age of 69, when he first took the brush in his hand and then he started painting, and his every painting is a masterpiece. Now today those paintings, they are sold in crores. So it happens. Nothing to worry about. In fact, I have already sent a mail to you that, well, I'm proud of you. This is a very good thing, that even say not worrying about that what would really happen or any of the negative thoughts, you are consistent with your passion. So very good. Nothing to worry about. It happens, and age is just a number. So don't worry about it. Okay. So it's all good. So welcome to today's topic, and that is action potential, right? So we started our journey by telling that, okay, this is the membrane potential, right? And in membrane potential, we divided it into two parts: resting membrane potential, which now I hope you know it very properly, right? And today we'll be talking about the action potential. Now, this action potential, it can be studied in under various subheadings. One is, say, when we talk about action potential in neurons, right? Then, when we'll talk about action potential in cardiac muscles, we'll talk about action potential in skeletal muscles, right? Because everywhere it is needed. And then there is one very nice, interesting part, and that is pacemaker. What really happens in pacemakers? Pacemaker means those who are initiating that pulse which keeps on heart beating, right? Especially say SA node, sinoatrial node and AV node. So in case if you don't know about it, nothing to worry. But these are some very special areas which will keep on sending the signals. And that is what keeps our heart beating, right? So we'll talk about all of them, but today we'll be starting with the neurons. ठीक? The neurons, if we really draw, that is quite nice, right? This is because it is quite irregular, right? So we just draw it like this. So they are all dendrites, right? Dendrites, which will be talking with other neurons. There would be a nucleus, right? So this one would be the nucleus, and this is the cell body, right? Cell body. So many things inside it. We'll talk about it. And then there would be axon, right? So this is what is called as the axon, right? In axon, and it could be very long, and then finally it would be again divided into what is called as all those vesicles will be here, and which will be releasing the neurotransmitter, and here it will be forming a junction with another neuron, and that's called as the synapse, right? In between we'll be having that myelin sheath, right? They will be myelinated because myelin is not giving only speed, but it is also allowing the impulse to travel for a longer distance, right? So this is myelin, right? In between these parts, so you already know, right? In between two myelin, this is called as the nodes of Ranvier, right? Nodes of Ranvier. Fair enough, right? So this was the cell, and this one is the whole thing is axon, and finally the myelins and the nodes of Ranvier. This is a basic structure, right? In this, what we need to remember is only two things. One, there would be, because these questions are sometimes asked, the way we have got rough endoplasmic reticulum, over here, in case of cell, they are called as the Niesel body, right? Niesel's body. So this is one you need to remember. This junction, it is called as the axon hillock. Axon hillock. This is the second thing. And obviously you need to remember about the myelin. These are the three important points which are to be remembered, right? Obviously, in case of where there is the nodes of Ranvier, there is no myelin. Now, apart from that, yes, myelin will be giving a protective sheath, etc. There is some very typical thing about these areas, and that is what we shall be discussing in depth, right? So, in nodes of Ranvier, I'm just changing the color and telling you to remember it. One, there is no myelin in nodes of Ranvier, and second most important thing, which is of our concern, is that sodium channels will be maximum. Right? Sodium channels will be maximum. And when the sodium channel is there, so then this sodium, what it will be doing, sodium is more outside, less inside, so that when the channel opens, that sodium would be gushing in, right? When that sodium, right, let's say this is that sodium channel, right? That's a cell. When it is gushing in, whatever the way that sodium channel opens, but when the sodium enters, so it will lead to more positivity towards inside the cell, because sodium itself is positive. It means technically we can say that nodes of Ranvier, because there are more number of sodium channels, it will help in doing dadagiri, right? So that means it will help in depolarization, right? Depolarization. Because more sodium channels are there. So sodium would enter, so cell will become from negative to positive, and from negative to positive, so that is depolarization, right? Everything so closely related. Perfect? Okay. On to the next point. Let's say this is cell surface, our neuron, right? If we put two electrode over here, so there won't be any potential recorded, right? No potential difference, because they both are onto the same voltage. No potential difference. This is one of the reason. Not understood connection between nodes and, okay. See, very easy. If we just zoom this thing, right? This is the axon. That's the myelin, right? This is the myelin. This point is called as nodes of Ranvier, right? Nodes of Ranvier. In nodes of Ranvier, there are more sodium channels, correct? More sodium channels. So now That's the cell, more number of sodium channels when at particular voltage, right? Because they will be voltage gated. When these sodium channels would open, right, there will be large amount of sodium which will be gushing into it because sodium is outside more. So this will, so over here they will be coming in. So now from this point onwards, so you know, Chirag, right? Because when more sodium is inside, so obviously that negativity would be decreased, it will go towards positive. So minus 2 plus, and that is called as the dipole, right? Depolarization. Good. Okay. So here, this is what we were talking about. Then when this is a cell, and then when we put both the electrodes onto the same surface, so there is no potential difference. This is one of the reasons when sometimes, say, you will see that on these electric poles, when the wires are there, and they are all high tension wires, right? And that's why on these high tension wires, in between, right, they keep the things like this. These are non-conductors, right? They are made up of such material which won't be transmitting any current. So this is to keep those two wires separate, right? So those high tension wires, they are going. Monkeys, right, they just hang on these wires, right? And they keep on moving from one point to another. They just jump over from here to here, here to here. It's because both the hands of monkey, they are handling or holding the same wire, so there is no potential difference. So that's why there won't be any electrocution, there won't be any electric current. But once when we were in Udaipur, I saw this thing, that when the monkey rolled and somehow his tail touched this second wire, and there was huge explosion, right? The severe electrocution. Bichara monkey, he literally burnt and he fell on the floor, right? I remember this thing because that monkey died. Right? And then suddenly, from nowhere, so many monkeys, they came over there, right? And they all were sitting silently. Means if you offer even banana, they won't even touch it. And yes, this is what I saw. And who tells that they are not sensitive? Right? Not a single monkey touched even a banana. After a few minutes, right, they dispersed and then they were back into their business. But yes, this is what really happened. So the point is that even on our cell, when we put two electrodes on the same surface, nothing happens. But when we do like this and this, one electrode inside and one on the surface, we see a potential difference, right? We see a potential difference, and there is a method also, we can measure it. We have talked about that our cell is more negative, right? So cell is more negative, and that is resting membrane potential, right? Which is normally, in case of say neurons, it is minus 70 millivolt, resting membrane potential. Now, this reminds us that why this is happening. Well, we have talked about it, right? Simply because potassium, right? It is the potassium who is responsible for this. And there is, in one word, if we say it is the passive diffusion, right? It is simply passive diffusion of potassium, efflux or influx. It has to be efflux, correct? Efflux. So when there is potassium efflux, potassium is going outside, right? So that cell is becoming negative, and this is minus 70 at this point, right? So from inside, yes, exit. So it is from in to out, right? In to out. That's what it really does. So that's the resting membrane potential. Just for the clarity, because these things will be, they have now started asking such things in exam also, that resting membrane potential. Now, you don't have to be extremely, means you don't have to do any rectification. But say for example, neurons, so it is roughly minus 70 millivolt, right? In case of skeletal muscles, right? Skeletal muscles, tomorrow when we'll be talking about it. So they are in the range of 85 90 millivolt. Same thing is in case of cardiac muscle, right? Cardiac muscles. So it is about 85 90 millivolt, right? Yeah. So these are the thing. Now in case of apna pacemaker, right? In case of pacemaker who is constantly sending those impulses without any motivation, right? Just completely self-motivated, and he is so restless. So that's why in that case it is RMP only, but it is not resting because he is never resting. That's why it is restless. Yeah, it is restless membrane potential. Restless membrane potential. So this ratification and all these words means who tells the doctors they don't have the control over language, right? They are also good in discovering new words. So this is like restless membrane potential. Right? Restless membrane potential means it is oscillating, right? It is constantly fluctuating, oscillating, or you can say it is fluctuating. It keeps on fluctuating. And why it happens? Well, tomorrow it would be turn of this, but just giving you this basic idea. So, and it is not even stable. So it will keep on fluctuating between minus 60 to minus 40, right? Minus 60 millivolt to minus 40 millivolt. So it will keep on moving. And this is the speciality of pacemaker, right? And obviously we say that where do we find these pacemakers? Now this is like a catch. This is like a catch. This is the thing which we need to remember. One, very easy, we say in heart, right? In heart, and in the form of SA node, in form of AV node, and even bundle of His, Purkinje fibers, they also do have very low activity of pacemaker. But then there is something more. You can find it in GIT also, right? GIT, there is enteric nervous system, and that is what is called as that who is the pacemaker in GIT? It is the interstitial cells of Cajal, right? Spelling is J, but it is pronounced as Cajal, right? It is interstitial cells of Cajal. Then even in respiratory system, right? In respiratory system, we know that that center is in medulla. So there must be some activity going into the medulla so that he keeps on sending the signal, "Arey boss, breathe. Arey boss, breathe." Right? Ruk jana nahi. Right? So he keeps on telling. So in case of medulla, also there are few pacemakers. Right? This is called as the pre-Botzinger complex. Right? Yeah. So that's the name, pre-Botzinger. But I used to remember it like pre-bought Zingur. So then it is right, but it is not Zingur, it is pre-bought Zinger. And for complex, we just write CX. Do remember this, right? This thing will give you a cutting edge that it is not so that pacemakers are only in heart, they are in GIT and in the respiratory system. And whenever such exceptional things come, these are the questions of all these competitive exam, right? So this is where they trick. So take care of this. Okay. Now I think you all know what exactly is the equilibrium, why there is need of other pacemaker if SA is there. Backup system, dost. Backup system. What if SA node fails for some reason? So then it is bye bye. Chalo, milte hain next janam mein, right? But heart tells कि no. When heart is so important, so he tells कि अच्छा SA node नहीं काम कर रहा, चलो AV node you take over. AV node is not working, अरे no problems. Even those Purkinje fibers will say कि चलो हम अपना काम कर लेते हैं थोड़ा थोड़ा, right? But keep the heart going. So this is like in our body there is amazing backup system, amazing backup systems, and these backup systems, they carry our entire body so effectively for years together, right? So we were talking about that equilibrium potential, right? Equilibrium potential. So in equilibrium potential, in single word, we say that there is no backup ka bhi backup. Oh yeah. So in equilibrium potential, recently I'm so tempted to make one video. When I read reduce your weight in 2 hours, and then there were like few million hits in a very short span of time. Well, that way to yaar, you can make a video that reduce your weight in 1 minute, right? Reduce your weight in 1 minute. Remove your t-shirt, right? Remove your trousers. But that's it, weight reduced. That's crazy. Means the titles are such. So anyway, coming back to this equilibrium potential. So in equilibrium potential, it is no effective, right? But what happens in that? Basically, we are losing water, right? You lose water. So that is such a temporary thing, and it is not even good for the body. So many things which are showed, right? It is not even good for the body. But yes, every time it's like, matlab pehle it was like reduce your weight in 1 month. So then there were, now then it came from 1 month to 1 week, 1 week to एक दिन से भी अब तो और कम. So equilibrium potential, that is no effective ion movement, right? There is no effective ion movement. As such, though it happens, but there is no effective, correct? No effective. It means whatever the ions which are coming, same amount is going. So everything is balanced, right? So when we say, this was the question which was asked. Right? Say equilibrium potential of sodium, that is plus, right, 60 millivolt, and we know all these calculations by, it is by Nernst equation, correct? It is by Nernst equation. Yeah, good logic. So sodium, right, that is having plus, it is by Nernst equation. Say in case of chloride, in case of chloride, that is about minus 70 millivolt. Now the question which was asked is, so the question which was asked is that equilibrium potential of chloride is equal to RMP of, question again, equilibrium potential of chloride is equal to, is same as resting membrane potential of, and then the option was neurons, skeletal muscle, cardiac muscle, pacemakers, right? You got the idea? So what they are asking is that you need to know both the things. Yeah, exactly, right? Because minus 70 millivolt is resting membrane potential of neuron, correct? So that's the thing. Perfect. So similarly, now we can say, we can create this question that, say for this potassium, right? For potassium, it is about 90 millivolt, right? 90 millivolt. And this is equivalent to skeletal muscles and the cardiac muscles, right? So if they have asked this question, they can ask this question. So in that anticipation, we have just prepared ourselves, right? And obviously the Nernst equation, which is for one ion, right? That Nernst equation, which was for one ion, and that was minus 61 upon Z, and the log of concentration of inside bindi and the concentration of outside. This was for one ion, and this Z was the charge, right? So in case of sodium, it is 1, and it is for the chlorine, it is 1, and obviously for the magnesium, it is 2, right? That's how it was there. And finally, for multiple ions, it was the Goldman, right? It was the Goldman equation. Okay. So far, all good, right? So this is just for the clarity, in case if someone has missed it. Now we go into the detail, right? What really happens, and then we'll draw the graph and we'll understand those concepts. So we have talked about neuron, right? Today, this would be our focus. We'll talk about neuron, and then we'll be talking about the pharmacology part also, right? Because it is pertaining to this. So it will make things more interesting. So this is neuron. In neuron, now we are focusing on, let's say this is our cell, right? This is our cell. All nasal bodies, and these are the dendrites. So we pick up one of the dendrite, this one. To this dendrite, some other neuron, right? It is coming and associating, right? So let's zoom that thing, because this junction is called as the synapse, right? It is called as the synapse. That is where two neurons, they talk with each other, but they are not in physical contact. They don't touch each other, right? There is a gap, and this is what is called as the synaptic cleft, synaptic gap, synaptic cleft, right? Synaptic cleft. So let's zoom this thing. Let's zoom this thing so that we come across that yes, there are two surfaces, right? There are two surfaces, right? This is what we have zoomed out. Okay. So over here on one side there would be vesicles. These vesicles, right? They will be filled with neurotransmitter. So they come and pop, right? They open, right? Top, and they release all those neurotransmitters. Once you have understood this thing, right? And then, so tomorrow we'll be talking about this skeletal muscle and cardiac. Day after tomorrow, my wish is to literally torture you. Torture you means how this entire synaptic communication, how it really occurs. I wish to teach all the 19 steps, because those 19 steps, they are mind boggling. But in that you will be learning about so many conspiracies, that what really happened at that airport when this brother of that Korean president was killed, how he was killed, what was given, right? How what exactly the things happened. That entire process, once you have understood, right? Yes, those 19 steps, they are slightly complicated, right? We might have to revise 2 3 times, but once you understand, trust me, you will be covering almost half of the pharmacology. Pharmacology will become so easy, and in any case, you have to learn those things. If not today, tomorrow you have to learn it. So why not to learn it in advance, right? Because it is all pertaining to this. Right now, all these concepts are fresh, so you will really relish it. So in other words, what we are telling is we are preparing for USMLE step 1. That's how we are going. That's how we are going. Right. So we are not learning only from the first year perspective, we are learning from the USMLE step 1 perspective. And as you must be aware that Pharmacology is a major portion. Pathology is a major portion, right? What we are learning, it is foundation. Based on this, everything would be mounted. Okay. Okay. So here there are receptors, right? These are all receptors. So these receptors, which receptors? We are not worrying about it right now. But these receptors, what will they do? These neurotransmitters, when they will come over here and they will come to in contact with these receptors, something would happen. Something would happen, and we know what would happen, right? The entire process. So these are all receptors which are ligand gated receptors, right? They would be GPCRs. That means they will be releasing something which will lead to opening of few channels, and for that we have already talked about, right? So these are the neurotransmitters, right? These are the neurotransmitters. Bas, this much we need to know, right? This much is sufficient. So this is like stimulation of ligand gated receptors, and they will change those ion channels. What change? They would open those channels. Bus, right? This is what will be happening now, right? So in neuron, things, if you see, this is neuron 1, this is neuron 2, and let's say if this is the axon, from here to here, it is the chemical neurotransmitter. Over here something happens so that this chemical is converted to electrical pulse, right? This chemical signal, right? Chemical signal is now converted to electrical signal, and on the axon, it is this electrical signal when it starts moving, and we call that thing as action potential, because it is running across the surface, right? Then it goes all the way till it reaches to the next neuron, right? It reaches to the next neuron, and then once again next neuron. For next neuron, this action potential is like electrical signal. So once this electrical signal comes, it will release some chemical, that is neurotransmitter, and then this neurotransmitter would be received by another neuron. Let's name it N3, right? Another neuron, this will receive. So again it will be converted to that electrical signal, right? That electrical signal will travel. So that is the action potential, and that's how things will keep on moving, right? That's how they will go, right? So this entire mechanism, right, it is a very intricate mechanism. So action potential is playing a major role in this. So here it is. And when we say that for ECF and ICF, right, we have got more sodium, domino like, right, more sodium, and this is like more potassium, right? Simple as that. And we also know that there is more chloride, right? Rest we are not touching right now. Yes, when it will come to muscles, calcium will also come into picture, but not right now, right? So we are just keeping calcium aside. This game is between sodium and potassium only, and partially when it will come, even the chloride would come into picture, right? So when things are stable, right, resting membrane potential, so it is about minus 70 millivolt, minus 70 millivolt. Okay, this is resting membrane potential. We are dealing with the neurons. Okay. Now when neurons are there, right, and the first we have to, because from the perspective of neuron, say this is one surface, right, and from here those neurotransmitters, they are released. They come, here is the receptor, they land over here, and it will lead to right, those changes. And first thing what would happen is that sodium channel, right, those sodium channel, that would really open. This sodium channel would open. So this sodium channel is what? This sodium channel is ligand gated, right? It is ligand gated because this thing activated because of this particular receptor, right, which is a ligand gated. Clear? But these ligand gated sodium, right, these ligand gated receptors, right, just let's keep this. These ligand gated receptors, which will be affecting the sodium channels, right? So that's why these sodium channels, we can say these are ligand gated sodium channels. That means they will operate when the specific ligand would come, but these are slow. These are not fast, right? These are slow. So that means there would be some fast channel. Yes, there would be few more sodium channels which will come and they will be like acting fast. So this is slow. This is a slow channel. So do remember, this is a slow channel. But whatever ligand has come and the sodium starts coming in. Sodium has entered, right? So sodium is now coming in. When the sodium starts coming in, first thing which would happen, that minus 70 millivolt, which was a resting membrane potential, now it would start going towards positive, not full positive, right? It will, or we can say it will start becoming less negative, right? Less negative. So let's say it comes to about, say, 65, right? So this means this is less negative. Less negative, yeah, more positive. But basically, it is going towards positive. So it is like our dada. So depolarization, simple, right? Depolarization. So now depolarization has started, right? But this is slow. This is slow because what is happening is that there is net influx of positive ions from outside into the cell. And why this thing has occurred? This thing has occurred because of that excitation, and this excitation is occurring after the synapse. Am I clear? Excitation was because of this neurotransmitter, right? So this was the exciting thing. Arey wah wah, neurotransmitter is coming. But who is getting excited? This is synapse. So in that we say this is presynaptic and this one is postsynaptic, right? Postsynaptic. Before synapse, after synapse. So that's why this voltage, this is a very interesting voltage. This potential is called as the EP, excitatory postsynaptic potential, EPSP, right? So this is because of that sodium which is slowly which will be entering, right? And later on we'll see that even this thing affects some calcium channels also. So even the calcium also comes in, right? This thing would affect even some of the potassium channels also. So potassium channels, so potassium will go in, go out. But what finally is positive ions, they will be in, right? So final is net influx of positive ions, right? Or cations. Net influx of cations. So that's why things have become towards more positive, right? And this is what is called as the EPSP, excitatory postsynaptic, right? Postsynaptic potential. Is this part clear? Right? EPSP. Because this EPSP is going to come again and again, right? Especially when we'll be talking about pharmacology. The way EPSP will come, similarly IPSP will come. That is inhibitory postsynaptic potential, right? So what happens in inhibitory postsynaptic potential? see something like this. Again, same drawing, right? This, this surface, and from here, say, this neurotransmitter is getting released, and for these neurotransmitters, say these are the specific receptors, and these neurotransmitters, they will land over here, and when they will land on this, so they will lead to stimulation of certain channels, and these channels this time, they are not sodium, they are not potassium. These channels, they are like for chloride. So this time chloride enters. When the chloride enters, it means cell will become more negative, right? Cell will go towards more electronegativity, right? Electronegative. So when it is electronegative, this is as good as repolarization, right? It is Rotlu, it will start crying, right? Because it is from negative to more negative, more negative. So that is what is called as the repolarization. It is a sort of repolarization. It means that even though the neurotransmitters were released, so which ion enter depends on type of ligand receptor. Perfect. Because it is the ligand who will decide that which channel to open. The neurotransmitters are same. So that's the fun, right? So these cells, right? These cells, they'll say, Acha, we want to, and that's why sympathetic and parasympathetic, right? Now see, the picture is becoming so clear, because sympathetic will say, what would you like to fire, right? They will say adrenaline, right? So epinephrine, norepinephrine, fire, dhan, right? Just go for excitation. Parasympathetic will say, Kare, why to do झगड़ा? Send acetylcholine. Acetylcholine say, अरे शांत शांत, सब बैठ जाओ, right? They are the neurotransmitter. Which neurotransmitter is released? Well, it depends upon the situation. So that's how they will go, right? So when we'll see in anatomy in more detail, we'll say that, okay, this is a parasympathetic system. This is a parasympathetic system, right? When we say sympathetic system, so we know that this is for fight, flight and fright response. When we say this is for parasympathetic, so we say it is for rest and digest. But who tells them that, अरे heart, आराम से बैठो, don't, no need to go for such strong powerful contraction repeatedly again and again. Parasympathetic. But how heart is knowing? Heart is knowing by these mechanisms, right? It is what is released is more important, right? So, and this thing will become crystal clear when you will understand that how these synaptic system they work, how there are various types of feedback mechanisms so that nothing goes out of control, and then how do they recycle the things. That was the best part of it. कि why to waste this neurotransmitter, है उसको वापस use कर लेंगे. So if it is not used, so then take it back and then next time we'll use it, right, as it is needed. So such a beautiful mechanism, and that's where the chemicals they enter, poisons they can enter, drugs they can enter, and when they block certain area, right, so that this transmitter, right, it is not functioning, or we stop the reabsorption of that transmitter, so that neurotransmitter it keeps on working. So that is how these medicines they work, right? That's why if you have understood this, the entire pharmacology becomes crystal clear. Suddenly you'll find, Arey wah, right? There is definitely an aha factor, right? As we study more. Acha. Today only, you just see after few minutes, you'll feel, Arey wah, this nerves, so they are so superb, right? You'll be so happy. Acha. So this is more negative to more negative, right? So from crying, from crying to bade aansu, right? Right. So that is repolarization, and as it is occurring, because when it is repolarized, that means this thing is as good as inhibiting it. You are stopping it. So it is called as IPSP, right? Everything happens at the postsynaptic junction, right? Postsynaptic zone. Nothing is happening at presynaptic. Presynaptic just decides what to release. Bus. So this is inhibitory post synaptic potential. Great. IPSP. So from this point onwards, when we say IPSP, do remember it is negative ions in flux. When we say EPSP, do remember it is the positive ions in flux. Which positive ions? Well, it depends. It depends what is available, right? It is acting on which gates, right? Because those gates, they will keep on changing depending upon the drugs, depending upon the toxins. But we understand one thing, that when the cations come, that is when the positive ions come, it is EPSP. When it is IPSP, it is the anions or the negative ions, they will be into influx. Fine. Okay. On to the next concept. There is, so we, how many channels we know? We know potassium channels. Potassium channels are like, they are passive, right? There are no gates, right? There is no stimulus needed, right? They keep on working, right? We talked about sodium channels. These sodium channels, they are ligand gated, right? Ligand gated. They are for EPSP. EPSP, which is slow, right? It is just to begin, just to start the whole process, right? It is like a trigger. It is like a trigger. Trigger means it is just to start, but it is not the accelerator. Accelerator is yet to come, right? So if I draw the graph, the graph would be something like this, that if this is our resting membrane potential, if it is our minus 70, right, this is our resting membrane potential, and it is at this point, and this is, let's say, minus 65, which is our EPSP, right, which is our EPSP, where, say, as this potassium, right, this potassium is leaking, right, it is also called as the leaky channels, right, they are the leaky channels. And then at one point, when the stimulus comes, right, the stimulus comes, when the stimulus comes, so these sodiums, they open, right, and they will reach to a new level, right. Let's say this level is minus 55. So here is the stimulus, that is the neurotransmitter has come, neurotransmitter, right. And at minus 55, this is, if it is a threshold potential. Threshold potential means what happens at this point is those voltage gated fast sodium channels, they enter. So we have got two. One, this was the slow sodium which was operated by ligand, and then we have got another sodium channel which is fast, and it is a voltage gated. So this voltage gated channel is operating at, let's say, minus 55 millivolt. So these channels, they say कि बस minus 55 तक ले आओ, बाकी तो will take the whole ground, right? But so this is what really happens, and that thing is called as the threshold potential, right? This is called as the threshold potential. So it is this threshold potential, when sodium, that is voltage gated sodium channels, they are going to open, and they are in large number. And now you know that at the nodes of Ranvier, if there are large number of sodium channels ready to fire, as soon as that voltage is reached, doom, 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 right, they will literally bombard the sodium inside, and straight away this thing will start rising, right? This is the thing, because this is nothing but dipole, right? Depolarization, the real depolarization. This is where our kite really starts flying, right? So if we say, and all these things, they occur in axon, right? Because in axon only those nodes of Ranvier, so they were there, right? So if we say that this is like our our axon, and if we say these are like nodes of, these are like myelin sheath. Now myelin sheath, this is like a cross section, that's why we are having, otherwise this sheath is around. If this is the axon, so then that sheath is like this covered, right? Full cover, right? In between space. So if it is a tube, right? So then myelin sheath is covering like this whole thing, right? Like whole thing. And in between, these are nodes of Ranvier. ठीक? So we just draw it like this, draw it like this, draw it like this. And here are, obviously these things are not in proportion, right? But let's say these are our sodium channels, right? These are our sodium channels. These are our sodium channels, right? So many. But there are no sodium channels into this area, right? So something different should occur at this point. Yeah, something different will occur, right? And these nodes of Ranvier, to so many, right? Literally, it would be studded with those channels, right? So again, over here, they would be studded with those sodium channels. Fine. So this is myelin. Okay? Myelin sheath. Just for the clarity, I'm writing myelin sheath. So as the voltage comes, right? So voltage comes, right? It travels. Here is first one, this one, right? He takes, okay, fire, thak, sodium in, right? Positive ions, shalom. Let's move further, right? The way we used to do, right? On the day of Holi, right? You come to my place with your bike, then I'll sit on your bike. We go to someone else, at a friend's place, right? Kal chal tu bhi apni bike le le. Then three of us, then three, they go to fourth person, and that's how finally to there is like a complete group, right? So this sodium fired. As the voltage is, right, they travel, there is a wave, right? There is a wave, positive ions, dhar, right? And then the entire group is moving. This is like a chain reaction. Right? This is like a chain reaction. One initiates second, two initiate third initiate, right? And that's how the action potential starts moving. Now, right now, I'm just drawing it like this. Actually, it is not like that, right? But just for the explanation, right? This is how the potential action potential moves, right? When the current moves, those sodium dum, right? They keep on coming in and the whole thing moves. This entire process is occurring at axon hillock, right? Axon hillock. Axon hillock was what? Axon hillock was the junction when the axon is meeting the cell, right? Do you remember? So this is the cell itself, right? It is just receiving everything and then it sends the signals to axon hillock where there are so many sodium channels, fast sodium channels. In cell, there were all slow sodium channels, which were activated by those, which were activated by those ligand, right? They were activated by the ligand. And these are all voltage gated, right? Voltage gated. So they move, right? So far, things are good. And it opens like talk, right? They keep on opening. But what myelin sheath contribute in moving them? Yes. Coming to that. This I did just to avoid one confusion, right? Myelin, we are coming to that. It is superb. It is amazing. So when this thing moves, obviously the whole thing moves to very much plus, right? So membrane potential, it reaches to plus 40, plus 50, right? Plus 40 millivolt. Because positive, and that's why we are calling it as depolarization, right? Depolarization. Okay. Now at one point, right? These voltage gated sodium channels, right? For the voltage gated, this is only for voltage gated sodium channels. There is something amazing. And this is for a crisp, clear clarity that it is not so that gated channels, they are only in two states, open and close, right? That we say that one state is closed, second is open, right? That's what we normally say. So this is like our channel, right, which is closed. Let's change the shape. It will become much easier to understand, right? Let's say this is closed, right? And then there is a gate also. There is a gate, but right now this gate is closed, right? The gates are closed. When we say it is open, so this is open. But there is a third state which is called as the inactive state. Inactive state. So in inactive, as such, the channel is open, but this door, it comes in a way and it blocks. This is the mechanism. Because in case of sodium channels, we said that there are doors, right? There are doors in and out. Right now, we are not talking about that out door. We are just talking about this door which is inside. So this inside door, it blocks. It blocks. It blocks it for some time. Why should it really block? Wonderful reason, right? Because it is giving time to this channel that you go back to, you reach to your resting membrane potential, and then we'll start the whole process again. What I mean to say is that this thing, right? Let's draw it. Let's write here. So this inactive mode, when it will occur? It will occur after depolarization. After depolarization. Till that point, no, it won't occur, right? So if you want to see the graph where it would occur, over here, right? It is this sodium is working. At this point, stimulus came, right? EPSP, right? That sodium came into picture, but this sodium is which one? It is that ligand wala, right? Then it would trigger whom? It will trigger voltage gated, right? Voltage gated sodium channels and this talk, and this is depolarization. When this depolarization is over, right? Depolarization is over, so then it will start for the repolarization. So it has to take a dip. But it is at this point, sodium channels are deactivated, right? They are not closed. Sodium channels, and which sodium channels? Those voltage gated, right? They are inactivated or deactivated. Now they will remain in this deactivated phase till you reach the resting membrane potential, right? So over here, so this after depolarization, they are deactivated and they will be coming back to this closed state, right? Once after RMP is reached. RMP is reached, resting membrane potential is reached. The advantage of this is that even if impulse it keeps on coming, the cell will not keep on firing, right? This will keep on firing under, means without any control. This gives a very nice control, right? Because during this phase, it is called as the refractory phase, right? We'll talk about this just a minute. Refractory phase. Refractory phase means even if you give a stimulus, there is no response. No response. This is called as the absolute refractory phase. It is because of this absolute refractory phase, things will not go overboard, right? It will not go into uncontrolled contractions. It will not go into uncontrolled firing of the action potential. It will control, right? Because one has to come to resting membrane potential, then and then the second stimulus can start. So this gives discipline. This gives decency. Yes, things will go in a controlled manner, right? Achha. When in refractory phase, if we say 1 is absolute, so second can be, which is called as the relative refractory period. Relative refractory period is that period that, yes, if a normal stimulus is given, right, no response, nil. But if a stronger stimulus is given, so yes, you get the response, right? So that is, both the phases will come in this. So we were talking about this, right? That it will go into the inactivated phase until the RMP is reached. So let's take our journey further, right? Coming back to this axon, that's our axon in which there were so many sodium channels, right? But now depolarization is over, right? Depolarization is over. So this means it is over. The moment depolarization is over, all our sodium channels, right? They are now into that block, right? Our sodium channels, they have blocked. We should draw it like this. It's though they are like open, but they are blocked, right? This will give us proper idea. So they are blocked. Bus, right? Same thing is at every level. It is at this point, at this height, right? When things are over there, the potassium gated, that is voltage gated potassium channels would start, right? This is at the highest peak, right? This is at the highest peak. So those potassiums, now they will start traveling out, right? Just to save time, I'm not drawing all the potassium channels, but do understand that these are all potassium channels, and these potassium channels, they are firing at the peak, let's say plus 40 millivolt, right? So at plus 40 millivolt, these potassium channels which are present into the axon, they fire. So right now the potassiums, they in fact they will come, right? They will start leaving, right? When they will start leaving, so cell is becoming more electronegative, right? So cell is going towards electronegativity, right? Because potassium is leaving, potassium is going out, right? So that leads to the fall, right? So if we really draw, so that leads to this, right? It is because of the potassium voltage gated channels, right? They are operating. Depolarization occur because of sodium, and repolarization because of potassium. Because of sodium, and obviously, this is, I read loss of, no, not loss, because, yeah. So it is because of sodium, right? And this slow one was because of ligand gated, and this fast one because of voltage gated, right? But basically, you are right, sodium. And this repolarization, that is because of the potassium, right? So this is now repolarization has started. So it starts dropping. One more thing which will contribute in this, and that would be apna all-time favorite sodium potassium pump, right? So let's draw this thing, right? This is our sodium potassium pump, right? He keeps on working dhire dhire, so he'll also contribute, right? Because he is throwing 3 sodiums out and taking two potassiums in, right? So that is, so what's really happening is generating -1 volt, -1 ion per cycle. So he is also helping this potassium, right? And the electronegativity, it starts developing. So now that when we draw the graph, we know that it falls, right? So this is at one point, at this point, literally over here. Yes, now I draw it like this. At this point, this is what is called as the absolute refractory period, right? Absolute refractory period. So this is when the moment sodium channels, they got deactivated, right? And this potassium channels, they are doing their business, right? You do whatever you want, but till the resting membrane potential is reached, nothing can be done, right? Nothing can be really done, right? Till the resting membrane potential is reached. So this green portion is our absolute refractory period. Is that good? Right? Because we only said that those channels, they will remain into blocked position till the resting membrane potential is reached. ठीक? Resting membrane potential is reached over here. Right? So when it is reached at that point, so we are happy, right? RMP is reached. So the absolute refractory period is now over, right? But because these channels, they'll keep on working, right? They'll keep on working. And so much so that potassium channels, right? Potassium channels, because of that free potassium channels, they are also working. Sodium potassium pump is also working, and these voltage gated sodium channels are also working. Now, voltage gated sodium channels will stop at RMP. But those free ka sodium channels, so they are working. Sodium potassium pump is working. All are enthusiastic. So this thing even dips further. It dips further. It dips further. And this phase is called as what? This phase, anyone? This phase, when it dips even below, it is called as, what was the name which was given to this? We learned that thing in case of hypokalemia. We learned that thing in case of hypokalemia. It is called as hyperpolarization, right? That's right. Yeah, you wrote it. That's right. It is hyperpolarization. Just let me show you. Yeah, you are right. You are right. Yes, here it is, right? This one. Hyperpolarization. When it dips more, right? When it dips more. So same thing occurs over here. So this is what is called as the hyperpolarization. Now see, in this hyperpolarization, from this point till it once again comes back to the resting membrane potential and ready to fire for the next time, right? When the RMP is reached. So this phase, this is called as the relative refractory period. This is the relative refractory phase, right? This one. It is relative refractory phase because now the reason is that at this junction, now the sodium channels, they are not blocked, but they are now closed. They are now closed. So if you send a strong signal, those channels will open and come shuru, right? So that's why it is called as, this is called as the relative refractory period, and this is called as the absolute refractory period or phase, relative phase, refractory phase. Good. So this is how that entire action potential moves. Now to add to this, let's not forget our myelin sheath, right? Our node of Ranvier and the myelin sheath. So once again, we draw our myelin sheath, but this time, right? This is our myelin sheath. Okay? This is our myelin sheath. And we said that in myelin sheaths, whenever there is myelin sheath, there are no channels, there are no sodium channels, nothing, right? So all those sodium channels, they are open, they are over here, they are over here, they are over here, right? Because this is like a very zoomed version. So obviously this part is node of Ranvier, right? This is node of Ranvier, this part, and this one is myelin. So here plus, 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 right? All those, they are coming. This is the next node of Ranvier. Next node of Ranvier. Now, whatever we say, this conduction, this action potential, the way it is going, right? Open, 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 channels open, open, and then the sodium comes, and then the things move. But it is a slow process, relatively, right? When it comes to nerves, so right, they should conduct the things at a very high pace. Our nerves conduct at the speed of about 75 meters per second. That's the speed, 75 meters per second, right? This was the reason that in cases of dinosaurs, this thing was very slow. So that's why even if some animal is eating the tail, right, after half an hour, the dinosaur would know that someone is eating my tail, right? Because the conduction was so slow, right? The way it is shown in Jurassic Park, right? But actually, in its real sense, those dinosaurs, they were very primitive. The size of their brain was very small as compared to the body, right? So over here, say this myelin sheath, because there are no gates, voltage jumps. This would be the word. Voltage jumps. Now, as such, they cannot jump, right? So the criteria is that there are positive ions. So this positive ion will push this ion, it will push this to this to this, it will push this ion will go out, right? Literally like a train, right? One dabba is pushing second, third, fourth, and then it is moving. That's how the entire system moves. All you have to consider is that the engine is at the last. So engine is pushing, right? And all the dabbas, they are pushing each other. There are no channels, right? No channels. Do remember this. There are no channels. So this system, sorry. So this system, the way it goes like this, right? There is a name which is given. It is called as the saltatory conduction, right? So this system in which these ions, they jump like this, it is called as the saltatory conduction. And this saltatory conduction, it actually improves the speed. It improves the speed, right? Let me parallelly keep on saving the file. Yeah. So this is how this actually moves into the myelin sheath. So you must have seen that it is like a combination of sodium channel, potassium channels, which are just taking it to the resting membrane potential. And then there is, if there is no excitation, to then bus, they'll keep on maintaining that resting membrane potential. But then comes the stimulus, which is in the form of neurotransmitter, right? Over here we have understood that it is in the form of neurotransmitter. Now we know that few gates they are temperature gated, few gates they are mechanically gated. Mechanical gated means when there is a touch, when there is a mechanical movement, right? So then it works, right? Few work on the principle of stretch. So if the things are stretched, so then they start changing the ionic mechanism. Whatever, all those gates, they are of different types. But if the stimulus is there, chalo, begin the process. And the process is what? Reach to the brain, right? So that's the reason when we talk it like this, right now we are talking about the sensory system. In our neural system, there is sensory. Sensory means any sensation, right? Any sensation, whether it is temperature, whether it is touch, whether it is pain, right? Whatever, carry it all the way to the brain. And in brain, there are specific areas which will understand, they will process, right? This is like a supercomputer which will process, okay, this signal has come from this particular region. It means someone is pricking this finger, right? To take the finger back. So what brain would do? Brain will tell, okay, all the muscles, अब तक कुछ काम नहीं कर रहे थे, चलो, you muscles, they are like, you are like my motor, right? This person is touching a very pointed surface. Tell him, tell the muscles, you take it back. So muscles would contract and then the hand would be taken back. So this is what is called as the motor system, right? Motor system. So motor system will be activating the muscles, and that's how things will move, right? This is the reason that when you are doing boxing, right? So if someone is giving the punch, so that's what it is called as reflex. These goalkeepers, right? It is like a reflex. So when they are getting the signals, the visual signals, that opposite person's, right, the way he is kicking, he is watching his leg, and when he hits, his brain would analyze at that point that in which direction the ball would come, and then the motor would fire that, okay, all the muscles on the left side, move the body to the left side and try to catch the ball. That's why penalty shootout is a mind game, right? It's a mind game. You have to enter into opposite person's mind, right? That if with my this movement, what he'll do. And this is the reason, it is one of the very fantastic science wherein ultra more than 200 frames per second, frame by frame, right? It is advanced, and then it is seen that when he started moving, then what happened to the goalkeeper. That's why you must have seen that they keep on shuffling right to left, left to right, right to left, so that that person who is shooting, right, the person who is taking the penalty stroke, right, he should not get the proper judgment that this person would stop at what point, right? So they do like this, right? And then it starts. This is the reason that when they said that the Messi, he took that penalty shot, and it was not at a very high speed, it was so slow. And that's when the commentator said, how can he do that, right? How he really enters into that person's mind, and he always takes him on the wrong foot, right? So this is the game of sensory and motor, right? But this is what really happens, right? That's why the medical is so amazing. Means at every stage, right, there would be the aha factor. Okay, wow, this is what is happening in our body. Yeah, actually, this is what is happening in your body, right? Let's make it still more interesting. Now, when we said, right, so we talked about refractory period, right? Refractory. Now, there are various books, refractory period, right? You will also come across one another term. It is called as the latent period. Means the same, right? Latent period. Latent or refractory, sorry, it means the same. Absolute and the relative. Okay? So, that's where the signals would come or no. Acha. Let's avoid this confusion. I'll explain it in a different way. Refractory, when we said absolute and relative. ठीक है? Absolute and relative refractory period. Latent, latent, actually what latent means? Latent means you give the stimulus and then you get the response. So this is, you can say this is like a delay, right? Forget about what I said before, right? No, take it this way. This is one concept, this is second concept. Let's make it very clear. Refractory means when you give signal, stimulus, no response, right? You give stronger stimulus and you get the response. Latent is a delay. You give even a normal signal, right? Normal stimulus, and then you get some response, but that time delay is called as the latent period, right? Latent period or the time delay, right? So that's how these things, they really go. Always nerve regains, right? Not only nerves, in fact all the cells, they finally they regain their resting membrane potential regained. So that's how the next cycle begins, right? This thing would always be there, right? After complete cycle, everything will be shuffled back to its original state, and then once again the second cycle would start, because then and then it can go with that much discipline. True, right? So in resting membrane potential, our potassium, right, it is the repolarization, right, it is the repolarization which is vital, correct, and that would always be because of potassium efflux, right, and then sodium potassium pump will take all things back to normal and the second round will start. Okay, so if we draw the graph, right, in which we add everything, so over here, right, so this is like our resting membrane potential, right? So from this point, if there is no stimulus, so then it will keep on moving to that level, right? Nothing would happen. Then you give a stimulus. After giving stimulus, for some time there is no response. So that would be called as the latent period. I'm trying to add everything in one figure, right? So that is called as the latent period. And then after that latent, there starts the first journey, right? So it will be taking it to, let's say this is, say it will take it to, let's say minus 65, right? Let's say this is minus 70, right? So minus 70. So this will be what is called as, because of the ligand gated sodiums, right? So I'll just write L, and it moves further, and at minus 55, so what happens that over here it is because of the voltage gated sodium, and it shoots, right, because these are fast. This thing is depolarization, correct, depolarization. Why it is happening? It is simply because of the sodium influx. Sodium is entering, right? From this point it is sharp, right, and then there is a gradual fall, right, gradual fall. This is what is called as the repolarization. Repolarization is because of the sodium efflux, right? Sodium efflux. Sodium is going out, right? Sodium efflux. And over here, what would happen to sodium channels, right? Sodium channels, they will be inactivated. But this you don't forget, right? It would be inactivated. It is simply because of this. There is the beginning. There is the beginning of absolute refractory period, right? Because this is when the sodium channels are inactivated, nothing can happen, right? So it comes. Then the resting membrane potential is achieved. It comes near, RMP comes near. So at this point, at RMP, right, those sodium channels, they are now not inactivated, but they come into the closed position. So it is from this point onwards, it becomes relative refractory, right? It becomes relative refractory. But who is responsible for this part, right? This over enthusiasm and going into hyperpolarization. Sodium, potassium efflux, so it is there, but then even the chlorine efflux starts, right? Chlorine influx starts. So that leads to that dip, and this dip is what is called as the hyperpolarization, right? Hyperpolarization. And from hyperpolarization, once again, it starts going those sodium potassium pumps, and everyone comes into towards the taking it towards the RMP, right? And say sodium, once again, it comes into its original state, right? And the cycle gets completed, right? So that's how they'll keep on moving. Just one word and immediately there would be complete clarity for the tomorrow. When I say depolarization, right? you could have asked this question that why we started with neuron. We could have started with smooth muscles. We could have started with cardiac muscles, right? But whether we start with smooth muscles or we talked with SA node, right? In all these cases, in case of depolarization is simply due to sodium. While in case of smooth muscles and SA node, it would be the calcium which would come into picture. So this I am just preparing your minds that tomorrow there will be one more entry, right? There will be one more channel who will be working, right? Now from where these calcium will come, that is where those endoplasmic reticulum and all those, they will come into picture. Got it? Right? So neuron was the easiest to understand, right? That's why we picked up. Now when the concepts are clear that what is absolutely, what is relative, what is fast sodium channel, what is slow sodium channel, what is ligand operated, what is voltage operated, right? Why this potassium, right? We can add this 1 point over here, right? 1.0 means in fact it is at the peak, right? But I'm writing it like this. It is the voltage gated potassium channel, correct? Voltage gated potassium channel. So when all these things are clear, right? Understanding cardiac, understanding the skeletal muscle, that would be crisp easy, right? Very, very easy. Acha. Something, say, histology is not very interesting, है ना? So time to time I'll keep on telling you, right? So when you want to, so that you remember it, this myelin, just remember a short, small piece of ratification, right? But again, not easy to remember. Acha. Do anyone remembers, say, which soap, right? Which soap is advertised by all those heroines, right? Those heroines, they are taking shower with that soap. The most popular soap. Most popular soap. Anyone? That's how I remembered it. Otherwise, it is very difficult, right? नाम भूल ही जाते हैं. Lux, exactly. See, you are like me. नहीं, Dove तो पता नहीं यार. Dove तो पता नहीं, but Lux is correct. Lux is correct. So because all of संतूर संतूर में कौन सी हीरोइन आती है? अरे बॉस, रियली? ओके. संतूर तो isn't it that ad? कौन सी कॉलेज में पढ़ती हो? If I'm not mistaken. I don't know. But anyway, Lux is popular, right? So this is Lux all, right? All the heroines, right? They advertise this. See, I know this part also. So myelin is stained by Luxol, right? Luxol stain, right? So Luxol stain. And obviously these advertisements, when they come, so people are in blue mood, right? So even this Luxol will also do that. It will stain myelin blue, right? This was one of the question, right? So do remember. Okay. So that's what we saw. Now from the clinical aspect, right? From clinical aspect. See, we learned action potential. Have you seen few people when they move like this very slowly, right? They speak also so slow, right? Their movements are also as if they are moving in slow motion, right? It's not their fault. This is what is called as the demyelinating disorder. So just think of any disease, right? Forget about which disease, right? Don't worry about it. But this is the myelin sheath, right? What if this myelin sheath is degenerated, right? It is degenerative myelin, right? Degenerative myelin. So if this myelin is degenerating, myelin was done, right? chalo, ions jump, right? Now that they will be slowed down, right? They will be slowed down. Now, why person should sodium will pass slow actually. Yeah, loss of speed. Exactly. Now, and you have said everything whatsoever is needed. Chirag and Siddhant, you have completed entire topic. Seriously. You have completed entire topic. First one, sodium will pass slow. And yes, to be precise, it is the loss of speed in saltatory conduction, right? Loss of speed in saltatory conduction. Yes, that is what would really happen, right? And why myelin to boss apna hi part hai. Why this should be degenerated? Autoimmune disorder, right? Autoimmune immune disorder. So body is not understanding that this myelin is not pardesi, right? Don't destroy, and it is destroying that myelin, right? And this is nothing but a very serious condition, what is called as the multiple sclerosis, right? So in multiple sclerosis, when the myelin is destroyed, so then it is that travel of sodium that slows down. There is decrease in speed of saltatory conduction, right? Saltatory conduction, and this leads to sluggish movement, right? Can I write sluggish? Sluggish means बहुत slow, sluggish movement. So even if you see when these persons they talk, right, they will talk so slow, very slow. Every word would come as if you are literally watching a slow motion, right? And even their walk is they will never run. Okay, okay, we'll talk about this. Just let me finish this part. Okay? So it will go in extremely sluggish movement, right? So that is what really happens in multiple sclerosis, because speed is by the presence of myelin, right? Acha. If this is the case, so how the myelin is formed, right? How the myelin is formed? Because myelin is what? Basically, myelin is a combination, right? It is a combination of lipid and protein. Now you know that. Now you remember it, right? It is the combination of lipid. Lipid was which one? Sphingomyelin, right? Sphingomyelin. You remember this, correct? And the protein, right? It is the sorry. So it is the protein, and this protein is myelin based protein, right? Basic protein, the basic protein. So that's how the myelin is actually there. And who would really produce those cells, right? So as such, we see this thing in embryology, but no worries, right? Myelin forming cells, right? So in myelin forming cells, all these are questions. Huh? All these are questions. But as such, when we try to discuss it, right, without any context, it becomes very complicated, right? Difficult to remember. Degenerative myelin cause of, yeah, yes. Acha. So myelin forming cells, in case of CNS, central nervous system, and in case of peripheral nervous system. Peripheral nervous system means nerves, right? Nerves. Central nervous system is brain and spinal cord. So in brain and spinal cord, we'll come across one type of cell. In histology, yes, we'll see these cells, right? But they are called as the oligodendrocytes, right? So when we say it oligodendrocytes, so these oligodendrocytes, they are doing what? They are making myelin. But these myelin, now listen, these myelin, the ratio is 1:30. That means they really pack those axons, right? So this means there is one axon, there is second axon, third, fourth, fifth, sixth, right? So many axons, and it would literally pack like this, like this. That's how the myelin would be formed, right? So myelin is in the ratio of 1:13. So one myelin and 30 axons, because this is central nervous system where things are very near to each other. So there is no point in individual ek, right? Pura pack, right? The pack of 30. So that is what happens in case of central nervous system oligodendrocytes. Function same, right? In case of PNS means peripheral nervous system, when individual nerves are going, right? So in that case, it is 1:1, right? And that is by Schwann cells. Schwann cells. S for single. Easy to remember. So single is 1, 1:1. So one myelin, one neuron, right? So single neuron, right? So that's how these things they really occur, right? So I think we stop at this point, and tomorrow we'll pick up almost from here, right? Almost from here, except there would be change in few ions, and tomorrow we'll talk more about the clinical aspect, right? So thank you so much, right? And we meet tomorrow same time, and we take the second part of it, right? Thank you and take care. See you tomorrow. Saving this file, putting into our folder so that you get it after just 2-3 minutes. Thanks and bye-bye.